Okay, moving on to the nitrogen compounds tutorial question 2. So question 2, in this case, we are looking at making phenylamine from nitrobenzene in the lab. So this is a very classic reaction involving nitrobenzene being reduced to phenylamine. So of course, in this reaction, you need your standard tin in excess corn hydrochloric acid. Okay, and then once the reaction is done, we then add in sodium hydroxide to neutralize it so that we can get pure phenylamine. Now, importantly, if you take a look at this setup involves us putting a condenser on top of a reaction flask. So one thing to note is that the condenser, the water comes in from here and then exits from here. What's the purpose of this condenser? It is basically to cool down any vapor that rises up due to the heating. So the vapor during reaction, as the reaction mixture is being heated, rises up and then it gets condensed and it falls back in. So this allows for prolonged heating of the reaction mixture, right, and prevents the drying out of the reaction mixture. In fact, this is your reflux setup. So to have a reflux setup, basically we put a condenser on top of a reaction flask. Alright, so the water goes in to cool down the vapor so that it recollects back. And then we have this apparatus on the side which contains a const of hydrochloric acid. You basically have this tap thing to control the flow rate. This is also known as a tap funnel or dropping funnel. It allows for us to have reagents addition to the reaction mixture in a very slow and controlled manner. Okay, so you will see this picture again in your lab manual. Alright, so you guys can familiarize yourself with some of the techniques that we use for organic synthesis. Okay, first part in A, we are supposed to write equations for the reduction of nitrobenzene. So nitrobenzene, NO2, to form NH2, phenylamine. So nitrobenzene to phenylamine. The question is, how many H's do we need? So some of you may be very simplistic. You think that, oh, you just need to replace the two H's to give NH2. But in fact, the oxygen here will also need to be reduced to form water. So 2 oxygen will give you 2 moles of water, and as a result, you need to total 6 hydrogen. Okay, so the conditions, tin, corn HCl, heat followed by NaOH. Okay, so in the second part, they say that explain why the acidic mixture must be made alkaline before the phenylamine can be separated out and purified. So earlier on, remember we added corn HCl. As a result, the H plus is present in the mixture. So what happens to your phenylamine is that your phenylamine, once it's formed, will not remain as phenylamine, because we know from question 1 that phenylamine is basic. So with the presence of H plus, it will form your protonated form of phenylamine. That means the NH3 plus. Okay, so in the acidic mixture, phenylamine exists as the NH3 plus ion, the protonated form. And this protonated form, because of it existing as ions, it is going to be more soluble in water. Because why? Because once you have ions, what kind of interaction can we form with water molecules? Alright, yes, you're right. This is your ion dipole interaction. Okay, so your ion dipole interaction will cause your phenylamine, the protonated form, to be very soluble. Okay, so the only way to convert it to something that can be separated out will, of course, you want to make it less soluble. So how do I make it less soluble? Is that when I add OH minus, the OH minus will then react with the H plus to form H2O, and then you get your phenylamine. Now take note, this phenylamine is going to be a lot less soluble. Why? Because of the bulky non-polar benzene ring. So once it's less soluble, it can then be separated out. Okay, so the bulky benzene ring cannot interact with water, so you expect the water to only form hydrogen bonds with the NH2 group, but it cannot surround the bulky benzene ring. Alright, as compared to your ion dipole. Ion dipole, this entire thing exists as an ion. Okay? Okay, moving on. We're supposed to calculate the percentage U of phenylamine. So we look at the quantities required. We have 4.84 grams of nitrobenzene. We know that tin is in excess, so that wouldn't be our consideration. We focus on the limiting reagent, 4.84 grams of nitrobenzene. Okay, so 4.84 grams of nitrobenzene, how many moles is that? We basically use mass over MR. Right, mass over MR. So mass over MR of nitrobenzene. So 6 carbons, 5 hydrogens, 1 N, 2 O's. You work out the number of moles, you get 0.0393 moles. We know from the equation that 1 mole of nitrobenzene will give you 1 mole of phenylamine. So it's a 1:1 mole ratio. The theoretical amount of phenylamine that can be formed will be the same, 0.0393 moles. The mass can be easily calculated via multiplying by the MR of phenylamine. This is the MR of phenylamine, which is C6H5 and H2. So this is the theoretical mass, which is the 100%. And what's the mass that we got? Only 2.64 grams. So 2.64 expressed as a percentage of 3.655. You convert to 100%, you get 72.2%. Okay, moving on to D. How will we confirm the presence of phenylamine? So phenylamine, one classic phenylamine test is to make use of your aqueous bromine at RTP. Alright, so what happens is that the decolorization of the orange aqueous bromine and the formation of white precipitate of the 2,4,6-tribromophenylamine. Alright, so take note, in this case you need 3 bromine atoms, you get tri-substituted product, and this will confirm the presence of phenylamine. Yes, it appears as a white PPT. Alright, your phenol, take note, your phenol, alright, will also work the same way. Right, so you have your 2,4,6-tribromophenol, you also have the decolorization of orange bromine, and you can also form the formation of the white PPT. Okay, so the question that I have for you as an extension, alright, how to distinguish between phenol and phenylamine. Okay, you can pause the video now and start thinking about it. We have gone through this before. We can make use of a very characteristic test for phenol, which is to add neutral iron 3 chloride. Alright, equals iron 3 chloride. You have a violet complex for phenol, and then phenylamine will have no violet complex. Okay, so although both of them will give you the same reaction with aqueous bromine, we still can find a way to distinguish phenol from phenylamine. Okay? Okay, with that we are done with question 2.